All right, well, today I'm going to continue on with Rick's theme, but talk about some of the implications in terms of what might happen from a biodiversity perspective, also what is happening in relation to climate change, and put some of it in context about the importance of interactions between various organisms. Now, the theme of this session is really changes in the boreal forest. And a lot of the changes that we see are human-related. Oil sands, energy development, pipeline development, forestry activities, agricultural conversion, and all of these things we know influence biodiversity. What we also know is that we've learned a lot about what different critters mean. So for those of you who were here last year, I presented on a variety of models that showed how various species of birds relate to forest age, forest type, how they react to edge, a bunch of stuff like that. We can now put those into models. Brad Stelfox is going to talk a lot about that this afternoon. We can make projections about what those birds are going to do now, in the future, as we change our land use planning. The nice thing about that, with a tool like that, we can start to plan. We can say, okay, we've got 1 million birds today, we're going to do this, that's going to lead to 500,000, that is or is not socially acceptable. We're now actually starting to integrate those into our land use plans. The Lower Athabasca used birds as indicators and built them into the system. It made some decisions about how many birds we actually wanted, where they were going to be, and how we were going to develop the various industrial sectors at the same time. But what we're not planning for, as Rick just demonstrated very clearly, is for climate change. We're talking about protecting for 50 years, 60 years, and making projections of how many birds are going to be related to human development. But that is happening at the same time that all of the things Rick just talked about are occurring. And so here we have, of course, get this right. Right there. Here we have Rick's, this is the world of today. That would be Lesser Slave Provincial Park. It's set aside. It's a wonderful place for protecting birds today. It's going to serve that role for 10, 20, 30 years, probably no problem. But when we go to the 2080s, we take Rick's hot scenario. The very place that is Lesser Slave Provincial Park is now in the Caribou Mountains. Is our planning of today taking into account, if our goal is long-term conservation, 100 years out, are we even planning in the right way? I'm not saying we are or we aren't. I think Rick's given you a lot to think about in terms of the potential risks that are involved, but I do think we have to start incorporating this into planning. Now, how do we actually do this? Well, the same models that I built and talked about last year can be used because we build climate into them too. We know that large-scale climatic variation is a driver of vegetation. The vegetation influences the birds, the bugs, everything else. And so we can use climate models to predict where animals are going to be, just like we can predict how to use it, and predict where plants are going to be. Now, there's a lot of assumptions with these approaches. The first is that biotic interactions are constant in space and time. What we see today is at some kind of stable equilibrium, and that what we see can be predicted and used to project the future. The second thing is that species can't adapt in place. And there is evidence that there is evolution, basically at a micro scale, happening in response to climate change in many parts of the world. So some species will adapt, some can't. The other one, and probably I think what's the most important, is that there's an assumption of no dispersal limitation. Animals and organisms can move perfectly in sync with climate. And we know that's not true, but we need to start thinking about what does that actually mean in terms of adaptation and conservation. So I just want to show you some of the extreme things that could happen from the perspective of birds. So this is some work by one of my students, Deanna Strahlberg. This is a bird called the bay-breasted warbler. It's usually found here in Alberta in stands 80 to 130 years of age, mixed wood to spruce dominated. It's found throughout, all the way across Canada. It's also found in parts of the United States and the eastern seaboard. You can see it's very common in Ontario. There's its distribution in Alberta. If we take Rick's, between his 2 and 4 degrees, we're kind of in the middle on this scenario. We're taking a 2 to 4 degree scenario. There's 2011 to 2040, where the climatically suitable space is for this bird. There it is, 2041 to 2070, and there it is by 2100. If our worry, our concern is conservation of the bay-breasted warbler in Alberta, and our policy is to protect it in Alberta, it more or less is now becoming the Caribou Mountains, our last hope for it. So we'll come back to that in a second. This is also not just about rare species. What's amazing is how climatically linked some of the most common species are. So this is the Tennessee warbler. It is a western boreal specialist. It's virtually found nowhere else, but it is probably one of the most common birds that we actually have here in Alberta and here in Western Canada. There's its distribution in the past 30 years, is what we assume. There it is 30 years later, there it is by 2070, and it is gone from this province. Its climatic envelope is gone. This is a bird that can tolerate a lot of stuff. It lives in shrubby vegetation, it can live in harvested cut blocks, it can live in old growth, but the climate space it's in is so tightly linked to the boreal environment that if we don't know the mechanism of why it's so tight, but if it is, and we use these projections, it's effectively gone. It's not even something we can conserve in the province in a climate change scenario. Now, it's not all about losers, though, right? And this is what we have to start thinking about from the perspective of invasive species. What will the heck will we mean by invasive in the future? This is an American goldfinch. It's native to North America. It likes prairie systems. It likes aspen parkland, chopped up little bits of prairie, pasture, all that kind of stuff. There it is today. There it is 20, 30 years from now. There it is in the 70, and there it is by 2100. Not a conservation issue. It's a big win for this species. The things it likes are going to be a lot more common. But technically, it's an invasive species in the boreal forest. What do we do about it? We don't generally, like in our policy right now, invasive species. We have to start thinking about that. One of the things that we've learned, and I think it's not just birds, Rick showed it just with the ecosystems, other students and people I'm working with have shown it with plants, is that these northern hill systems in the boreal forest, the Caribou Mountains, the Stony Mountain, things that we call mountains, that are really only a couple hundred meters in elevation higher than the rest of the boreal plains, become particularly important as potential conservation areas. Big reality check, though. All of those models are predicated on the assumption of equilibrium. The climate will change, the animals will move with it. The reality check is climate change is going to change biotic interactions, and it's going to change them a lot. Now, there's a lot of ways that this might happen. I just want to walk through a couple of ideas and show you some examples of where things are going. So we have more carbon emissions. That we know, we're doing it, maybe we'll get it under control. We also have a lot of land use change. That land use change can influence climate change in a whole bunch of ways. One, we change the vegetation, we change the carbon storage capacity of our ecosystems. The agricultural systems do not store as much carbon as forests, okay? So we're losing carbon storage capacity. On top of it, a lot of our land use activities are influencing the distribution of these invasive species. It's not just human land use that influences whether an invasive species will get in. Climate change plays a role, but there's an interaction there. If we make it easier for species to get in, species can invade in systems, they have an influence on the vegetation, that alters climate change or carbon carrying capacity, and we get all kinds of things that are going to be invasive. And as this cartoon says, oh, I just know this is going to mess with the ecosystem, and that's the whole point. Invasive, non-native, or if we just think of them, the new species that are coming are going to change the biotic relationships, and they're going to change them a lot. So this is a scenario that's in a paper that was recently published in Frontiers in Ecology and Evolution talking about savannification of Western Canada. In other words, the boreal transition, where we are, the aspen parkland, where we're standing today, is likely to become more common further north, and we're going to dry out, as Rick just showed, further south. Now, a lot of the mechanisms that Rick talked about are things like more fires, more windstorms, pests, things like mountain pine beetle. Those are all things that, we're already starting to see or be concerned about. But there's a whole bunch of other interactions that people are also starting to see related to the new species that are showing up. And I want to talk about two today: white-tailed deer and exotic earthworms. So, for those of you who don't know, and this is a lot of people, during the last glacial extent, so about 11,000 years ago, that red line was where the glaciers were. All earthworms from North America, not all of North America, but Alberta in particular, were extirpated. They're gone. Right? And its reason being they couldn't have survived that many years, thousands of years under the ice. So we have earthworms in the southern United States. We also have a ton of them still left in Europe. Europeans come, and guess what? The earthworms start to spread, and they spread with European settlement. Right now, there are about 8 species of earthworms in Alberta's boreal forest. None of them are native. They're all non-native. The reality is, when you go in the boreal forest, those creatures have been put there by mechanisms that we have influenced. And this is to prove it to you. So here we have the proportion of sites occupied by earthworms, and we have a variety of locations throughout the forest. Campgrounds in boreal Alberta, there's an 80% chance you'll find earthworms at them. There's about an 80% chance you'll find one on or adjacent to a well pad. There's about a 70% chance you'll find one near a road, 50% chance near a pipeline, 20% near seismic. And if you go into the bush 300 to 400 meters away from any human disturbance, there's a less than 10% chance. I'm going to argue that's pretty damn clear evidence that humans have some kind of relationship with it. Now, what's the mechanism? Campgrounds, we believe, is fishermen abandoning earthworms as bait when they're done fishing at the end of the day. There is strong evidence for this based on the composition of the species that are there. The well pads and the roads, we believe, is due to soil disturbance and the moving around of dirt from place A to place B. And as well, roads, earthworms more or less, they reproduce through something called a cocoon. So think it's a tiny little pop rock candy, and there's could be 11, 12 juvenile earthworms in one of those. If a single one gets dropped off, it's an instant population, and the species that we have most commonly doesn't require sex to reproduce. It can instantaneously start a population and start breeding. The point is, earthworms are changing, or not changing, but earthworms are in the system. We've got proof of that right now. Are they spreading? Well, this is a picture of the earthworm distribution near a 10-year-old road in northern Alberta. There's another 10-year-old road. There's another 10-year-old road. You can see they're right up against the road. You get into the bush, they're not there. Here's a 40-year-old road. That's the distribution of the earthworms. That's another one. That's another one. The earthworms are moving throughout the system. Now, why on earth should we care? And I'll come back also to what this has to do with climate change in just a minute. That is a soil horizon in Minnesota without earthworms. That is a soil horizon in Minnesota after earthworms invaded. They are very different. The most fundamental difference, the leaf litter is completely changed. It's being pulled down through the soil layers, it's being mixed together, and we are getting a very narrow, thin leaf litter now on top where earthworms are present, whereas when they are not present, you have nice stratification with very thick leaf litter and very well-defined soil horizons. The consequence of that, and I won't go into the reasons, is that our understory plants are changing quite dramatically. Now, back to climate change. What does this have to do? Well, it is assumed, remember, that the glaciers were the reason earthworms weren't in the system. So the second assumption is that the permafrost is also what stops them from going too far north. We have evidence that we're way past the permafrost line now. So somehow earthworms are being able to make it. And their populations are increasing. In Minnesota, where these pictures are taken from, they have very significant concerns. There are species of plants and birds that are declining because of earthworms. It could very well be that the increased temperatures, different changes in winter temperatures in particular, may be allowing earthworms to do much, much better. Here's where there's a very scary, though, and a very compelling thing to think about. So here what we have is carbon, okay, in megagrams per hectare. And what we're talking about here is a scenario of what are the effects of earthworms on carbon storage capacity of the boreal forest. All right? And this is a scenario that's looking at the time in years sense of disturbance. Okay? And what we have is we're thinking about fire. So this is actually the Canadian Forest Service fire model. And what it's showing is that after you have a fire, you have a buildup in the amount of carbon that's being stored simply because the leaf litter is starting to reaccumulate after the fire. And then it slowly starts to degrade as the forest gets older and older. So, you know, how many leaves and how much carbon we're storing in a forest depends on its age and a variety of things like that. That's the fire scenario. This is the scenario with fire and earthworms. Earthworms actually have a huge potential impact on the ability of the boreal forest to store carbon and has big implications for Kyoto, well, not Kyoto because we didn't sign Kyoto and we got out of Kyoto, but basically, a lot of climate change agreements have, you know, the ability of your forest to store carbon as a credit. This mechanism could change that pretty fundamentally. Now if we take a look at it, roads are influencing earthworms. Earthworms are influencing carbon storage. Here's the Alpaca FMA up here in northeastern Alberta. This is a projected development road network with those spread rates of earthworms that we've just established. By 2056, we would suggest that about 40% of Alpaca is going to have earthworms based on our road build trajectory, rates of invasion, and rates of things that are going on. The amount of carbon that's going to be lost as a consequence is a vast number. It's so big I don't even know what it means, but the point is it has huge potential implications. And so there's a feedback loop here. We've created these linear features. They allow in a species that alters carbon. Carbon influences the ability of the climate, of systems to be resilient to climate change. So it's not just people's effect on climate change, it's the way the biotic interactions, interplay with people. Now, from a perspective of, let's go back to the birds. So the birds, when you look at it, we said, those models suggest, all biotic interactions will be the same. Well, what we found is, in fact, this is my kindergarten science project, by the way, American robins like earthworms. Everybody knows that. Well, if you now look at the distribution of American robins in the boreal forest, they like campgrounds, they like wet pads, they like roads, they like pipelines, they like seismic lines, and they like interiors. So is that just a correlation? Well, I guess I forgot to put in a slide I was thinking earlier. But the point is, the only time you find robins is when you find the earthworms. Robins are competitors with other birds. So there are going to be changing interactions whereby an invasive species is getting in due to climate change, that alters another bird's distribution, which then could influence another bird that it has to interact with. Now here's another scenario that I think is starting to play out in Alberta as well. So we've probably all heard that white-tailed deer are expanding. I'm going to show you an example to demonstrate it. But in the eastern part of North America, what they've also found is that the two things are happening simultaneously. Earthworm populations are coming up. They're causing a lot of degradation of the forest understory. Deer populations are exploding, in part due to climate change that I'm going to try to demonstrate. And the two things combined are having a massive effect on the ability of, again, carbon storage, understory plant cover, and which obviously has implications for birds and other organisms in the system. So Kim Daw, who's a student with myself and Stan Booten, wanted to demonstrate to people that deer have and are changing. This is a map that shows in the 1970s the probability that you would find a deer basically at about an area of about the size of a township in the forested systems of Alberta. And this just shows you the probability that you would have observed. That's the 1980s, the 1990s, the 2000s, the 2010s. That's real data. That's how deer have changed over the presence of them over that time period. You take that model, you project it out based on just the linear trajectory and the change in something that I'll come back to in a second called the winter severity index for white-tailed deer. There's the 2020s, 2030s, 2040s, 2050s. White-tailed deer are going to expand in this system with climate change. Why? Because of this. This red line is what's known as the winter severity index. It's a great predictor of deer's ability to survive the winter. That red line was below it. That was conditions which deer could survive the winter in Alberta and have decent populations. Above that line, it's real hard for deer to make it. Snow's too deep, it's too cold, they don't cut it. They're not boreal creatures. That's where that line was in the 1990s. If you think, and you're one of those people like me who says to their kids, come on, let's go outside, it's not that cold out. And they're like, it's freezing, Daddy. No, it's not. When I was a kid, it was 10 times colder. It's true. It was 10 times colder when I was a kid. All right, it was way colder. The point is, deer are changing. What does that have for implications? Well, let's look at it. Here we have all of the caribou ranges across Alberta in the 2000s. In the background, we have some estimates of where the deer will be. There's the 2050s. Deer interactions with wolves and moose and caribou are one of the primary reasons that we have an issue with caribou right now. It's not just the human disturbances. Human disturbances don't kill caribou. Wolves kill caribou, and wolves kill caribou when there's more of them. When there's more of them, that's because they have more food. What's that food? It's caribou a little bit, it's moose quite a bit, and it's increasingly white-tailed deer. So our deer populations are influencing many, many things in the ecosystem. So in summary, I guess what I just want to highlight, and I think what Rick has done a very good job, climate has changed in Alberta already. It has since the hypsothermal, it has in the last 100 years, and it's going to continue for sure. I've shown you some examples of some of the biological consequences. I think we can probably go with expect the unexpected. There are things that are going to change, but I don't think that should stop us from planning, right? I think things like these hill systems, from a conservation perspective, we really have to start looking at them. Right now, we don't even worry about them. There's basically been no biodiversity surveys in half of them. So these are places that I think we might want to think about protection both from a land use perspective and also climate change as we move forward. So with that, I'll stop and take any questions.
I just wanted to quickly point out there's a couple microphones throughout the room that you can go to for your questions.
Seems like you don't believe me. Well, I'll be around if there are any questions.
Thank you, Dr. Bain. We're going to have a quick health break right away here. I didn't point out that there's bathrooms through these doors for men's and women's. Also, I wanted to